Hi everyone, this is Dr. Hopkins with the third and last video describing the properties of lanthanides. As you recall, in the last video we talked about the electronic structure. In this one we're going to describe the spectroscopy of the 4F to 4F electrons in lanthanides. Alright, so we're going to slowly walk through this. This is brief. So we're just looking at 4F to 4F transitions. There are obviously other electronic transitions that you can get spectroscopically, but the primary ones that we use are intra-configurational. Okay, so the line strength of this transition, assuming that all other mechanisms are small, so this line strength D, that gives us the intensity of a particular transition between A and B. So A and B would be our two 4F electronic states defined by our 2s plus 1 LJ uh, term symbols. Okay, so maybe it's from 5D0 to 7F0 in europium. So those would be our two states. The mu effective is the electric dipole moment operator. Now, I say effective electric dipole moment operator because strictly speaking, F to F transitions are parity forbidden. Okay, so that means they're to the first order they're forbidden, but you can get some electric dipole transition intensity based on mixing and so forth. And then the M is our magnetic dipole operator. So this has to do with either the electric dipole moment within the molecule or the magnetic dipole moment within the molecule. Okay. And both of these operators combine the structure of the ligands around the lanthanide itself. Now, the magnetic dipole moment operator oftentimes can be just from the lanthanide ion itself, but the electric dipole moment requires an interaction between the metal and the ligands. Okay, so we're the crystal field of the ligands. All right. And so if we have that gives us our line strength, how large a line would be. Now, if we look at the selection rules based on our term symbols from between A and B, you can see that we have delta S. And so we're on the left, we have our electric dipole transition. We should have no change in spin. We have to have less than 6 change in the orbital angular momentum. And then that adds up to a less than 6 change in the delta J. Now, if J is equal to 0, so if one of the states is equal to 0, then you only get delta J 2, 4, and 6 for electric dipole transitions. And then the magnetic dipole selection rules you see are delta S, delta L. Now, clearly the L and S are not good because we do see in europium 5D0 to 7F0 or 7F1, right? So we're clearly changing spin, we're clearly changing L. So those selection rules are relaxed because S and L are typically not good quantum numbers. We've actually coupled S and L together to make J. So we consider J to be our primary quantum number driving selection rules. Okay, so we have delta J less than 6 and delta J equals 0 plus or minus 1 for magnetic dipole transitions, and those are the allowed transitions. So if we look at the europium 3 plus, the emitting state is 5D0, so we're primarily talking about emission. So the J equals 0. So going from 5D0 to 7F0, the delta J is equal to 0. Okay, so we go back to our selection rules, and in both cases, you noticed as J is equal to 0, we can't get magnetic dipole allowed, we don't get electric dipole allowed, and we typically don't see that transition. And then you can see the 5D0 to 7F1 is magnetic dipole allowed, but not electric dipole allowed. The 0 to 2 and 0 to 4 are both electric dipole allowed, not magnetic dipole allowed. And then our 0 to 3 is not allowed by either one. And so if we look at a spectrum, you'll see exactly what we just showed in terms of our selection rules. Down here at the 0 to 0 would fall somewhere in the 580 range. There's a small peak there, but it's not allowed, so we don't see it. The 5D0 to 7F1, we see that's our magnetic dipole allowed, and then we see our 0 to 2, 0 to 4, but we don't see the 0 to 3. All right, we see a very small peak at the 0 to 3. So it follows those selection rules in general. All right, so then if we are doing circularly or chiroptical spectra, like circularly polarized luminescence, so we're talking about emission and circularly polarized luminescence, and that's one of the things we measure in this lab, the intensity of those transitions as opposed to the emission or the luminescence that I just showed, the intensity of the CPL is defined by the rotatory strength. So basically it's just the product of the transition moment for the electric dipole times the magnetic dipole. So in order to have rotatory strength, you have to have both, okay, in terms of that. And so you can imagine if you have a very large electric dipole strength, a very small magnetic dipole strength, so you have a very large transition, you would also get a pretty large rotatory strength. It's not an indication that we have a lot of circular polarization in the emission. It just is a recognition that, hey, we've got more photons coming out, so more of them are polarized in general. All right, so we normalize our spectra for that in terms of the dissymmetry factor, this GEM, which is basically the 2 times the CPL, but it actually ends up being the circularly polarized luminescence divided by the average of the total luminescence, so the sum of the left plus right. If we summarize those in terms of our matrix or the photophysics of what drives intensity of each of them, it's basically 4 times the rotatory strength over the dipole strength. So if we have something that is predominantly electric dipole, the intensity mechanism, so for example, 5D0 to 7F2 in europium, then the dissymmetry factor is driven by the intensity of the magnetic dipole transition and how small the electric dipole transition is. So the larger this is, the smaller this is, the larger our dissymmetry factor is going to be. And it's also based on the angle between the magnetic dipole moment and the electric dipole moment of the particular molecule. Okay, so that's a structurally based factor. If it's magnetic dipole, predominantly magnetic dipole transition, then it's the opposite. Then the larger the electric dipole transition is, the larger we get in terms of dissymmetry. The smaller our magnetic, the larger, and then once again the angle based on the structure. Okay, so that's, for example, in the 5D0 to 7F1 transition. And so if we go to a spectrum, if we look at this, this is one shown from, we published this in 2016, and basically it's a europium triflate. We put in an ionic liquid and we let it interact with the chiral parts of the ionic liquid. But he showed both the 0 to 2, the electric dipole transition, okay, we can see we have much more intensity in the red, which is the total luminescence spectrum. It's an electric dipole transition, we get more intensity. And then the magnetic dipole transition, it's a little less intensity in the red down below. You can see that both of these show CPL spectra. So the 0 to 1, the purely magnetic dipole transition, has to get electric dipole intensity somewhere. And that comes from the fact that there is mixing between, say, the 7F1 state and maybe the 7F2 state. So you get J to J mixing within the actual set of term symbols. Okay, so you have to have something that gives it some electric dipole transition, and the more electric dipole transition that you get into that, the larger the rotatory strength is, then the larger the dissymmetry factor is. And likewise, the same thing, the 0 to 2 is an electric dipole. There's not magnetic dipole allowed, but there's J to J mixing. So there's mixing between these two states that allows for you to get a rotatory strength, okay? And you can see that, and actually what drives that JJ mixing is the structure. How are the ligands arranged around this europium, okay? And in this case, we're showing the 2 chiral components of proline in the blue and the green, and you can see that as we change the sign, we're changing this. We change the handedness of the ligand. We're changing the sign of the CPL. And one other thing you'll notice is that typically the dissymmetry factor for a magnetic dipole transition is about a magnitude, order of magnitude larger, in the 0 to 1, then the 0 to 2. And some of this has to do with the fact that the electric dipole transition is very small for that. But basically, that's what we're doing when we're putting together these ligands and we get CPL. We're generating a structure that allows these transitions to mix to ideally generate circularly polarized luminescence.